So let us go through the various properties of Z transform. The very first property is the linearity property. In linearity property, we say that if there is a signal x1n whose Z transform is x1z, there's a signal x2n with Z transform x2z, and if I now give you a third signal x3n which is expressed as linear combination of x1 and x2, which is ax1n plus bx2n. Linear combination is nothing but addition or subtraction of the two signals along with the scaling factor. So a and b will be some constants. Now in this case I may not find Z transform of x3n separately. All I have to do is take the same linear combination for x1z and x2z. So x3z, which is Z transform of x3 of n, will be nothing but ax1z plus bx2z. So that's a linearity property which is very simple but very important also. This tells us that the Z transform is linear in nature and hence it can only be applied to linear systems. I cannot apply Z transform to non-linear systems. And for the same reason, whenever we use Z transform for the analysis of discrete time systems, we have to assume that the systems are linear in nature, which is possible for most of the practical systems which fall under the scope of our discussion. The next property is time shift property, which is also very important, because in any practical system, when we apply the input signal and when we try to analyze the output signal, the signals are often in time shifted form. So in this case, the property says if we have a signal x of n with the corresponding Z transform x of z, then if we shift the signal x of n minus n naught, if I shift the signal by n naught, in that case the corresponding Z transform you'll have to multiply by z raised to minus n naught to x of z. So you can find out the new Z transform by simply multiplying with z raised to minus n naught. Moving on to the third property, which is of time reversal. In time reversal property, we say that if you take signal x of minus n, its corresponding Z transform will be nothing but x of z inverse. That means x of z, which is the original Z transform of x of n, and if you perform x of minus n, which is also called folding operation, all you have to do is replace z with z inverse in the corresponding Z transform. Moving on to the next property, it is of scaling property. So let us say if I scale the signal with a raised to n, that means if I multiply the original signal with a raised to n, this is my scaling factor. In that case, my new Z transform becomes x of z by a. So everywhere z will be replaced with z by a. If you multiply by a raised to n x of n, you replace z with z by a. So a simple example of this property could be in this form. Suppose if I simply multiply my signal with x of minus 1 raised to n. If I multiply with minus 1 raised to n, if I compare it with this property, that means my a is nothing but minus 1. So the corresponding Z transform will become x of z upon minus 1, which will be nothing but x of minus z. So x of minus z will have the inverse Z transform of minus 1 raised to n x of n. Please do not confuse x of minus z with x of z inverse. Both are very much different. Here you replace z with z inverse. Here you simply change the sign of the z term. You don't inverse the z variable.